Hello, everyone. This is Benjamin. Welcome back for another Tech Talk. This time, I think we did good. The previous Tech Talk was only last week, right? So let's try and keep to this schedule. Quick reminder that if you would like to be on the show, for the lack of a better word, if you would like to present something, we don't have to call it a show and make it more important than it is. But let's discuss. Like ping me, and if you have some interesting topics, it doesn't have to be fully like Zephyr related, as long as it's cool, technical, embedded topics. Let's chat and let's share with the audience. So as always. Let's have a quick round of intros, maybe, and hear from you guys in the audience where you're joining us from. I'm joining from France, as always, or as I am most of the times. And we have many folks already lining up. I think the turnout should be really good today. So Joël, I'm guessing, is joining from France. Let's hear about others. And today the topic is going to be Rust, and more specifically Rust and Zephyr. So I myself don't know much about Rust. So as often with those tech talks, I'm going to use this hour as an excuse to learn more. I think some of you joining might also be more like Zephyr people more than you are Rust people. We'll try to learn more about what Rust is in the first place, why it's relevant for embedded, and how you can use it on top of or together with Zephyr. Because again, many of you, that's why you're here for, right? So let's bring in our guest as often as always, and this time is no exception. No slides or hardly any slides, so it's going to be all about answering your questions, and I'm sure there will be many. David, welcome back. It's been only a week since you were on the show, right?
Yeah, it's nice to find a slot so we can kind of continue where we left off from last time, I think.
And maybe you can quickly tell us or remind us who you are, and we can just dive in the discussion.
Sure thing. So I work for Linaro, have been there about 9 years. Started doing Linux kernel stuff, moved to Zephyr pretty early on. Have been involved in Zephyr. It's like 6-7 years, something like that. And then most recently, it's about 6 months or so, I have been working on this Rust on Zephyr project. Just to kind of a little background, I am being paid for this work, so it's kind of a nice get this little season of somebody wanting to get Rust support kind of more officially into Zephyr. There have been a few kind of various projects doing it in various measures, and I thought this would be a good opportunity to get something that's like actually in the tree and, runs through CI. There's a lot of things like that where when it, as we've discovered it recently, it points out things that go wrong fairly quickly that we have to fix. But
yeah, this work is really new, right? Like, and I think many people now sort of recognize you. But yeah, like it's only a few weeks since it's effectively sort of like officially available. Still sort of like an optional feature, but was made available as part of the Zephyr 4.1 release, which went out about a month ago, right? And
there was actually like the shell was in place in 4.0 to kind of the mechanics of it, but it wasn't useful for anything. I mean, you could run Hello World and that was it. Now we have a pretty significant amount of what is available in Zephyr that you can do. I will point out, however, that this is continuing and ongoing work. And if you want to really get involved with it, I don't recommend sticking with the module that's in 4.1. It's best to go to main on the Zephyr on the module. There's not anything yet that would keep that from running with 4.1 though. There's no changes to Zephyr that have been going in that affect this. So
right, yep. Yeah, well, and I guess speaking, and we have really lots of people today. So folks, start lining up your questions. I mean, we're barely getting started, but I'm sure some of you might be more maybe advanced in your sort of Rust journey, and you might have some burning questions. So please line them up. But yeah, you were mentioning sort of like a few months back, you were only getting the Hello World, and that's basically it. I guess we can start there. Like for
Sure thing.
folks who don't know much about the language, not even speaking about Rust in the context of embedded, like just Rust in general. Like, what are some of the like, how does it
Sure
taste
thing.
like?
So
Not taste rusty, but
a little bit of background. I've actually been using Rust for well before the 1.0 release, which is
which would have been how many
oh,
years back?
that's a
5+ right? Or
that's a good question. I don't actually know the answer to that. I will
yeah, never mind.
that
But
off
it's
so we can
like
get an
it's
answer.
a,
2015
I
was
guess my
what,
point is like it's more than like a yes, it's
11
the new
years.
kid on the block in many ways, but it's been there for many years already, right?
Yeah, so the project actually started way back in like 2006 or so,
Right.
2009 or so was the first release. And before 1.0, there was a significant number of language changes. One of the things that I have liked about the language is there's been an amazing amount of stability for the language. They have currently there's now 3 what are known as additions, which are changes to the language itself over time. And they're just numbered by the year of the edition. The current one is 2024. Not a lot of code is switched to that. But what's fascinating about it is the compiler supports every edition. And when you bring in dependencies, each dependency states the edition that it's built for. And it's perfectly happy to compile all of these together into an application. So you don't need to update old code for the new editions. At the same time, you can make your new code work with the edition. I will point out, however, that the current code, I do depend on fairly recent things in the Rust language. So you're best off making sure to use the latest stable compiler. That's been a goal, is to not depend on the unstable compiler. If anyone's familiar with what went into the Linux Rust support on the Linux kernel, is they started with the unstable kernel or unstable Rust compiler and have actually added language features in the process of doing that, several of which are now stable and I depend upon. So there's kind of
Right.
all of this is a bit new in the sense of making use of kind of fairly low level programming in Rust. It started out with a main focus of, desktop and server type applications for web development, for web backends typically, or processing, all kind of it's a pretty general purpose. Maybe an overview just of the language. The main thing that it brings from a programming perspective, as far as programming language goes, I don't know exactly what it would be most like for people. The syntax is a little bit different, but semantically it's still very similar to C, C++, that type of programming language. The main thing that it brings is what's known as memory safety without garbage collection, that the language at compile time validates that pointers are still valid, that you can't have pointers to things that then go out of scope and are, like a pointer to something on the stack, go out of scope will be a compile error and that kind of thing. In addition, it has things that are similar to what C++ provides of zero cost abstractions, that you get higher level constructs of, you can have methods on types and even kind of dispatch and that kind of thing that doesn't cost you anything at runtime. The compiler is pretty sophisticated. I guess the other really big benefit is very strong typing, which is probably the biggest thing that makes it differ from C and C++. Well, C++ is pretty strongly typed, but you can create abstractions. And we bring this out as we start to talk about things like device drivers in Zephyr, that instead of this struct device that works across any device, I have different types for the different kinds of devices, and they have methods appropriate for that device. And lots of other things going on there. There is a movement for, it's called Rust-Embedded. There's a thing called the Embedded book about doing embedded Rust on bare metal, where they do Rust programming directly using HALs and some simple kind of scheduling support that's available. And we can get to that later on in the talk, why a lot of that code is actually really useful to us when using Rust on Zephyr still. But as can be imagined, there's a lot of boards that aren't supported. There's a lot of functionality there's a growing effort that's definitely happening there. But Zephyr brings us an enormous number of boards, hardware, devices, subsystems that exist, that are tested. There's a strong community and ecosystem around them. And to be able to combine that with some of the features of Rust, especially memory safety being the big one, that you don't have things like buffer overflows, invalid pointers. There's a lot of, from a security perspective, a lot of the things that you find as vulnerabilities, especially in C code, a lot of those would be caught at compile time in Rust. And that doesn't mean it doesn't keep you from writing bad code. It just takes a whole class of bugs and moves them to things that become compile errors instead of runtime errors and potentially security issues. I don't know if you wanted to dive in with a little Hello World example.
Yeah, I think that would be a good starting point. Yeah.
So I've got a share up with some code, and we got an awful error message that we won't worry too much about because we're not going to be navigating too much of the code. So this is about as simple a program as you can get on Zephyr that still uses some interesting functionality. First thing that's going to stand out is this declaration here of no standard. So just quick syntax. The hashmark bracket syntax is an annotation. It adds an attribute to some aspect of the program. The ones with the exclamation point apply to the contained entity. So this is telling us that this entire module in this file, sourcelib.rs, has this no standard flag set. And what that means is that we're not using the standard library. Standard library is typically either POSIX or Windows based. There are some efforts that people make to use standard on embedded systems. I'm actually going to be doing a blog post coming up as to why I don't think that's the best answer. The biggest thing is that standard makes a fairly pervasive assumption that memory allocation is the way to do things. And that's not usually how we do a lot of stuff in embedded. There is memory allocation, it's available, but you tend to want things to be static and more deterministic than that. Setting that aside, many of the arguments against dynamic allocation don't apply with Rust. You have much better ways to manage things like memory leaks and invalid pointers. So actually using dynamic memory is not an issue, but we do try to avoid it in the support, although there's a bunch of features that still are dependent on that I'm still working on. Going on from there, this use says in some other module, I want to use from this, what's a top level thing is called a crate. So this is other code called log. The log is kind of a semi-official crate for doing logging inside of Rust. We can get more into the interesting mismatch between Zephyr logging and Rust logging. Right now, what happens when you log messages in Rust is they just become, it depends on how it's built. If you don't have logging on, it ends up calling print K. If you do have logging on, it does log through Zephyr's logging. So from there, right now, I do this manually. I'm probably going to use features of the Rust language called macros that would allow this to look more like just a declaration of a main. But the no mangle says leave this name, the symbol, as actually Rust _ main, because this is going to get called from C code in Zephyr to start the Rust code. So we're telling it this is use the C ABI for this function called Rust main. We then call this function in. So the Zephyr crate is the one that I provide that gives the interface to all of as much of Zephyr's API as makes sense. There is a function in there called setLogger. There's a long discussion as to why that's unsafe, that we don't necessarily need to go in. One of the things that Rust requires is anything that doesn't meet the language's strict memory safety requirements must be decorated with this block called unsafe. And there's a handful of things that are still marked that way because of it was difficult to make those work in Rust code with the way that the API works. And then from there, we call the regular Rust logging macro info, which works with their formatting strings. But a couple things that are pointed out, does my cursor? Yes, it does. This kconfig module is generated by the build system, and this config board, anything that is a string or numeric type, shows up in this module, and you can refer to them in your code and you get the values of them. You can even do conditional compilation based on kconfigs and stuff. So what this program does, it doesn't do anything to build it because we already built it. I don't know if you want to see the build and comment on how slow it is.
Yeah, I was gonna.
Because that's been one of the interesting comments. So this is kind of a normal Zephyr build if you're used to that, except it runs along until it hits usually this step, and then it just sits there because of the interaction with the way CMake works. It doesn't print anything out until it's done with the entire Rust build. If anyone is brilliant with CMake, feel free to, tell me what's going on there or help me fix that.
Or would it make sense, just like we do, say, for the C standard library with like Pico libc, to have pre-built like
no.
scene-based critical
the
section,
simple
whatever?
answer, the simple answer is no. There's a lot of stuff that will get cached here, though.
Yeah,
So
it felt like it was faster than what we did right before going on the air.
Yes, you may find it's very slow the first time you build, and then it's not as bad from then on. There is a lot of code. If you notice this list of stuff that's compiled and brought in, much of this code is actually running at build time. It doesn't clearly tell you what that is, but this crate here called Zephyr build is what converts the kconfig values, the device tree, and these things at build time into Rust source code, so that when you access Zephyr functions and stuff, they're actually generated from your config with the header files in the exact version of Zephyr you're running by a tool called BindGen that turns these into it. It's a lot of code, as you can see here. This is auto-generated from the Zephyr header files, and you don't really need to look at it, but it's there. If we do a run, we get hello world, and it ran just fine.
So we might have, I don't know if that's the solution, but Johannes on LinkedIn is saying that for showing progress, maybe it's as simple as setting use this terminal in CMake to show output. I don't know.
I will look into how that happens, and or how to do that. I will make a note so that I remember to do that. And then we can also go here, for example. So this is a thing I use to build for lots and lots of different things. If we come in here and pick, say, a Cortex M3, this gives you an idea of what the build time would be like. So this is actually a different Rust toolchain. It's a different architecture now, and the decision as to what version, how to configure the Rust compiler is chosen by, there's a CMake deals with that. As someone was asking earlier, what boards and platforms are supported. Right now, this works on a handful of Cortex M platforms, and it also works on RISC-V, 32 and 64 bits under QEMU. I don't actually have any hardware to try that on, but
I guess another way to ask the question is, so this handful of M0s, what does it take to support a new board? For some, it's just a matter of testing, right? And
so generally what happens is typically when you add a new board, you will try it and it will fail fairly quickly. Usually what has to happen is if you go into, what is the file called? There's a file here, DT Rust. So this is a YAML file that describes, so there's some information missing from the device tree. When the device tree is used by C code, a lot of the knowledge of, for example, what kind of device uses a particular node is just embedded in C code that happens to say, I've implement this, and we need something in Rust to tell us what API to use for a given device. Most of the time, for the small number of devices that we support, it's often the flash controller. Usually you just have to add your target's flash controller to this list. Given that flash controllers and GPIOs are the only things that are supported, that's usually sufficient for this to work. The nice thing is then when we add other types of hardware that might be vendor board specific, the tests will start showing the failures, because the samples currently list a small set of targets that we do build for, the ones that I've mentioned, and then I build for one particular board that I had sitting around. I have another board that I build regularly for that I realized is not actually in tree. So that's a task for me. I need to actually upstream the board support for this board. Well, actually, it's my own board. I don't think it's worth upstreaming the board support for one that I am the only person on the planet that owns one of those boards. So that's not as useful. So there's a bunch of questions that have come in.
Yeah. And speaking of support for platforms, is there a plan, or what is the plan for Embedded-hal support in Zephyr? And maybe you can tell.
Yeah, so let's step back and say what is Embedded-hal?
The Rust community didn't wait for Zephyr to start doing embedded, right? They have their own efforts, right?
Well, so Embedded-hal is actually a very specific thing. So to define some terms, there's something called a crate in Rust, which is a unit of compilation. It might be considered like a package in some programming languages. It's a library. It might map to like a shared library in C or that kind of thing. It's a unit of code that's distributed independently, and in my program, I can depend directly upon it. Embedded-hal defines a bunch of what are known in Rust as traits. The closest thing you could think of a trait would be like an interface in an object-oriented language. It defines a set of methods that must be implemented for something that then other code can use in a generic sense without having to know the specific kind of device. So as far as Embedded-hal support goes, it is desired. So as far as the status of the project goes, the initial focus of this effort has been on the core OS support. So threads, scheduling primitives, memory management, logging, this kind of thing. And the device support we have right now is very minimal. I have basically the ability to toggle pins on a GPIO. I do have some stuff. I've started some things with I2C, and there's a little bit with UART. So not a lot yet as far as what Embedded-hal, but that's kind of an obvious next step of where to take things. That when we do create an interface in Zephyr or in the Rust on Zephyr support for a given device interface, the API defined by Embedded-hal makes the most sense. There's actually a handful of crates. There's Embedded-hal. There's also an Embedded-hal Async, and we'll get make sure we don't forget that, but we should spend a little bit of time talking about Async and how that fits in with Zephyr. So what I would say is the plan is to support that, that when it makes sense to use that, to use the Embedded-hal API. On the other hand, I will say, if you're familiar with some of the other embedded Rust, generally the HALs themselves implement the Embedded-hal interface and then give you a bunch of other functions, because the Embedded-hal is kind of minimalistic. It's a kind of least common denominator. But yeah, why don't we go on to some of the other questions? There's one about memory consumption that might be useful to. So it's a little hard to answer the question like in a general sense, because it depends on what you do.
And maybe just taking a step back, like the Hello World that you built, it's not fully Rust, right? Like it's like most of it is actually C, like actual Zephyr
most
objects.
of it's the Zephyr code. It's the Zephyr core, the Zephyr kernel that comes in, and then within. Let's see. I don't think that script is here, but if we go to my keyboard for, well, actually that's not a good place to look, because that one, I don't have that working. So I don't have that thing working yet. But if you just do a West build, we can, of course it doesn't do anything because CMake is too smart. So we'll put a 2 in there. So right now we're using 35K of code for this program. And roughly, I'm curious if this will work. So for those who know a little bit about Rust, there is a, we have an error that it's not working because this file is missing. So I'm going to make a directory called .cargo here. Oh no, it exists. So there's a file that's generated by the build, by CMake. Oops, let me turn my alarm off. This is normally when I wake up. The build system generates this TOML file that configures, this is how what all the stuff that needs to happen for Cargo to be able to actually build this program standalone, which means that I can actually do things like this. This is doing a check. And what this means is that you can actually just run your IDE here. When I run my editor here, and I'll have to figure out why that's failing, because it shouldn't be failing, but we can run the regular tools. It also allows me to do this. None of these things would work. So there's some issues with how this gets built. So yeah, there's a lot of little tooling things that would be helpful for figuring out the sizes and that kind of thing. Roughly when I last looked at it, I think the Rust core that comes in is like 10 or 15 kilobytes. it depends on the functionality. If you use logging, you will pull in formatting, and that adds its own, it's like 8 or 10.
And you're talking code size, right? I think the question was specifically about RAM. Like, is this
right? So that's actually
more? I mean, but
that's
that
more
was
minimal
useful
in
feedback.
that sense. The RAM usage there we're looking at is 10 kilobytes for this Hello World program, but I believe most of that are things like the stacks and things that are predefined in there. There's very little that the Rust code right now is using as far as RAM goes until you start defining your own things that make use of RAM. So yes, the RAM is pretty similar to just doing Zephyr applications. It does bring in more code, so having a microcontroller with a little bit more flash than you might expect is probably going to be helpful. As said, I typically will build. We should just look at this file because cargo.toml is the top level file when you build a Rust application. This defines the crate of my app. Right now, it's defined as this thing called a static lib, so that we actually generate a .a file for the Rust code, which is then linked by Zephyr. And then we're dependent upon the Zephyr module, which is defined as part of the build. The build system makes it so that that's available. And then I'm pulling in log. But you can actually add any dependency that's in the crate ecosystem here. As long as it works in a no standard environment, you can pull it in just fine. As an example, there's an example here of bringing code from the Embassy project into a Zephyr application.
So yeah, tell us more and tell me more.
Sure.
I hear about Embassy a lot. I mean, you guys are really active on Discord, for example, and I know you mentioned it recently. There's also a question actually in the chat. When one has an hybrid Zephyr plus Rust project, would you recommend Embassy Executor or the Zephyr static thread tools? So yeah, what is it? It's basically a scheduler independent from what we have already in Zephyr, or
it's a little complicated to explain what is going on with async. So this started to solve a problem of like server applications that make an enormous number of network connections, where having a thread per network connection is overwhelming. The cost of a thread, in addition to scheduling resources, is a stack. You need to have enough stack space for that thread to hold the deepest call stack that happens while that thread is in progress. So what async does is you have a keyword in your code. When you say function, blah, 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 you can say async function. The compiler, instead of generating a traditional call frame where it calls and returns, it returns this thing called a future, which is effectively a state machine that is invoked and runs until the program needs to wait for something. And then it returns pending, and there's a mechanism to wake that up later. It's done through just simple function calls. What this means is that many of these asynchronous tasks can run on a single thread. So as far as do you use Zephyr threads or do you use async? And I don't necessarily have a solid answer to that. There's kind of an almost philosophical difference in terms of how you do that. I mean, to answer the question for a very practical case, I developed my own keyboard firmware. It makes extensive use of async. And in fact, it only has 2 threads. So the issue there is async. The async threads are scheduled kind of themselves. There's a little bit of a scheduler, but it's very small. It just walks through a linked list and runs the next one. It's very lightweight. You only need the one stack. The state is stored in these statically declared structures, but it's cooperative. If something does start using the CPU, it won't run a different thread. And that actually is kind of exactly what happens if you have threads at the same priority in Zephyr. So it makes sense to have like two threads at different priorities, and you have a lower priority one that uses a lot of CPU, and then the higher priority one that handles I/O operations. So this example here, I can pull in the Embassy project. So Embassy is a project it's a bunch of utilities for doing initially bare metal Rust code on embedded systems. But it includes a bunch of things that are actually work just fine inside of Zephyr. I implement just to give you an idea here, we implement this executor in Rust, and it doesn't fit on the screen with this large font, but it is literally 80 lines of code, which includes all of the comments, all of the headers at the top. And this is just, its only purpose in Zephyr is to say, as a thread, I have nothing more to do. Please stop running so other threads can run. And then when the wake call gets called, it will then wake up the thread so that it can then continue running. And then the other thing I provide is using Zephyr timers, a timer that works with Embassy. It implements Embassy's time driver so that anything that's expecting the Embassy APIs for async, for timing, all of that stuff ends up just working. As far as which one you use, it kind of depends on your application. And it's a kind of an architecture of how you build an application. Do you build lots of little async threads that communicate with each other via messages, or do you have a handful of threads that block and do other things that would be kind of a more traditional how you would do that in C? And for a given application, it's probably one of those where we're going to be kind of learning as people start writing applications, which of these is best. I mean, I'm taking the approach of let's make sure both of these work. There's a question briefly just about, can the Embassy executor run on Linux? Yes, but it's unrelated to this. Sort of, there is a patch to make the native sim, the POSIX native target work on Zephyr, which would then give you both of those. Everything that you're doing in Zephyr would work just fine on your Linux machine in that case. And that all just works. The executor doesn't really know anything about what's going on your system. There's a question about power management. The simple answer right now is that we don't do anything specific other than, like in async, we make sure the thread isn't running if it's not doing anything. And you're left with the power management that happens when you hit the idle thread. Beyond that, it's going to start to become various device drivers. And are we making sure that the interfaces and such that we use with those drivers work? I mean, the issue with power management generally is to make sure that you know when to sleep. So that would have to be done with code, and that you don't spin, you don't sit there using CPU that you don't need to and prevent the system from going to sleep. Practically speaking of my keyboard controller, that although my keyboard firmware is running currently on a USB device, I do hope to get Bluetooth working at some point. I went through a bunch of analysis of what it was running, and in a couple of days, I went from over 100% CPU to just a couple percent of the CPU when you type, and it doesn't do anything when you're not actually typing. It's completely idle. And so I don't think there's anything Rust specific about that you still have to do the same kinds of things, but it is an important concern to make sure that the APIs for driver interfaces and stuff don't have loops that spin. I think that's probably the biggest thing from our implementation that we make sure we don't do. And given that most drivers are still to be implemented, as something to do. I don't know if that answered your questions about async, or if you wanted me to talk any more about that, Benjamin. I don't. You're muted.
Yes, thanks. Some people commented that there's some echo, so I'm double muting myself.
Okay.
I think what I would like to us to talk about a bit is more the and there's a question I can pull it up. The interaction with the devices, like we've seen Hello World. Can we look at Blinky maybe, or like something like interacting with
Sure.
GPIOs and device tree, and what does that mean in terms of getting?
So, let me
better
answer the
type
question
safety
directly
as well,
first, and then we can look at specifics.
Sure. Yeah.
So the question is, should each of them be ported as Rust traits, methods manually? And I would say so can Rust code directly use the drivers from the Zephyr C code base? The answer to that is yes. Anything that is in the header file you can use from Rust code. There's a few instances. If you want to show the share again, there's a couple of instances where bindgen isn't smart enough to export a symbol. It usually happens if it's a pound define where there's an expression as the thing. So I have a handful of symbols that I just forward to. I stick them in consts, and then it knows, oh, look, I can export this as a value because it knows it has to be constant. But otherwise, this wrapper file is a bunch of pound includes that allow the code to access any kind of C functions. And you will need to, the main issue with this is you lose a lot of the benefit of Rust when you do that. However, I will give a caveat. For example, again, back to the keyboard firmware, because that's the practical thing that I'm working on. That has a lot of things that I have not written Rust drivers for, Rust wrappers. It does USB, for example. And in that case, I have my own kind of thinner wrappers that are very specific to what I'm doing that work fine. It's so in this instance, I actually have a little bit of C code that interfaces to it. And then, so this one, I wasn't even using the new, this was before I wrote the driver for GPIOs. And so this is actually just calling the Zephyr functionality directly. And this is kind of an example. It's similar to what you would write for the wrappers. But what I would say is we would like as a goal to have Rust-style wrappers for most of the drivers, which allows them to be used in a much more natural sense. You'd mentioned Blinky. So in this case, and I don't know why it's failing, but in this case, this is what you get as an example here. So first of all, this is telling us compile this code in if there is a device tree node aliases LED0. And this is a direct mapping of the tree from the device tree with the slashes replaced with the module separator in Rust, which is : And if this exists, we compile this code, and I just say Zephyr device tree aliases LED0 get instance. And this gives me a GPIO pin, which if my IDE was working, I could hit this and it would show us the type, but I don't know what's going on, why that's failing right now. And then I'm actually getting rid of the GPIO token mechanism because it makes it too hard to use. And And then I just say LED configure. Currently, these have to be unsafe because of debates going on in the amongst the. From a Rust pure perspective, the GPIO interface is not safe to use because there's no concurrency guarantee from it. What I'm thinking of is making it the get instance will be unsafe, and then the rest of it will be safe. So we basically configure the GPIO. We call toggle pin on it. This is just kind of a direct mapping to Zephyr's interface for that, and then we sleep. And then there's another thing that just does nothing if there's no LED configured, so this will build on the QEMU targets and stuff. This obviously is a very simplistic device. As an example, if you enable the async code, I have this method called wait for high, which can be used asynchronously, and this will actually, it registers a callback from the IRQ with the Zephyr GPIO driver subsystem, and then when that pin goes high, causes this thread to start running again. And so this code can actually deal with the GPIO interrupt in a way that looks like it's just waiting. And so these are the kind of things that make the code a lot easier to use once the wrappers are written, that they're kind of more natural, that I can just say wait for high, that kind of thing. In fact, once I get rid of the GPIO token, this thing that does wait for high, I can actually say, oh, I'd actually like to wait for any of these pins. And then the async code has this thing called select, which basically says wait for any of these things, and then it returns the one. And the little Rust binding takes care of, in a sense, translating that to how, the Zephyr callback from the GPIO driver is just one function that it calls, and it figures out which ones of these can be awoken, I think is the better.
Yeah, and this is where maybe, back to the power management discussion, this is where maybe it doesn't work. Not everything might work automatically. Maybe if the language is smart in that sense, then maybe that might actually have impacts on.
So in this case, this actually works better from a power management point of view, because the thread, if it has nothing else to do, will then go to sleep. And then when the callback happens, that will wake it up so that it can then run the next piece of code, so that the code isn't, for example, waking up periodically to check the GPIO. It just waits. Now,
yeah, I guess I was more thinking beyond the code and the kernel aspect of it, more about like the power management of the actual peripherals impacted. Okay. Like, I don't know if that...
Well, and that's kind of where, for example, Embedded-hal, it's nice to have the HAL interface so that you can call these different functions, is high, is low on a GPIO, or read from a device, or kind of thing. But we do need to also provide other aspects of the API that Zephyr provides that are needed for power management. This GPIO, stop driving it. This controller, put it to sleep. That kind of thing. Those interfaces do need to be still exposed so that power management can be done in that sense.
Do you want to take the question about
this is a really good one.
Yeah.
So you're looking at GPIO right now, which I'm still trying to figure out how to make that more usable without unsafe. I'm going to try. I originally wrote it to not require unsafe, and I got a lot of pushback from people telling me the GPIO driver itself is unsafe. For other devices, that's not going to be as much of an issue, because the problem with the GPIO driver is there's other parts of Zephyr that I don't have control over that use GPIO, other devices and that kind of thing. And because of that, I can't use Rust's mechanisms to just guarantee one instance. Rust has a really nice thing that if you have a reference to something that's mutable, it's guaranteed there's only one of those. But that doesn't work if there's C code elsewhere that's still using it. So that's kind of the problem with GPIO. I'm probably going to just make it so you call unsafe once to get the GPIO and say, yeah, I know the GPIO is unsafe, but then using it is going to just be regular methods. But other devices, I don't intend for you to have to use unsafe throughout the code. Because as you point out, yeah, that kind of defeats a lot of the point of using Rust. Obviously, we need unsafe where we directly interface with Zephyr. But one of the benefits of having those wrappers is that it presents a safe interface. A good example of where that works I have a port of the Dining Philosophers example. And in here, there is these synchronous channels which are implemented on top of KQ in Zephyr. And all of this code, there is no instance of unsafe anywhere in this file. And it is able to use bounded, unbounded channels. This started out as an attempt to make something that worked like the standard libraries communication channels that work on top of Zephyr. And I mean, it works, but because it's modeled after the API from standard, it depends on alloc a lot. So I don't know if it's the best solution for that. We probably want to we may want to implement something. Well, a simple example is if you're using Async, you can actually just use the channels that come with Embassy. They would just work. You don't have to, there's no porting, none of that stuff. Those can just be used directly. Or from other projects. The nice thing that especially Async does is it separates the OS implementation of how you do scheduling from the operations that you can perform, and it allows you to implement what might be thought of as low-level things in a completely OS agnostic way. So there's just a lot of code out there that we can just use with that. I don't know if that really answers the question or not. The goal is no unsafe, but we're still in the process of getting there.
Yeah, sounds good. So we are almost 5 minutes before the end. So Joe, and I'm sure others share the same, say thank you for all the work to get Rust and Zephyr to this point, which kind of brings me to a question in terms of what's next. As you mentioned, and as a reminder, there's already a lot that's happened in the past month since Zephyr 4.1 was released, and people who want to be on the sort of bleeding edge might want to check out main, basically. But yeah, what's next, and two, how can people help and engage?
So what's next? So the most obvious thing is I have a pull request open that may turn into a couple of pull requests, depending on how reviews go, of a handful of additional features that I've been working on to kind of wrap some of this up. Most of them are more hygienic. That initially, for example, to declare threads was this really complicated, messy thing. Now, when you implement threads, I did not convert this example, but oh, that's right. It's in a tree it's in a PR, not in the current branch. Is there no force? No, I guess I could just stash. Instead of the weird, messy macro, to use threads now, you can just say an attribute on a function that says, oh, this is a Zephyr thread. Here's its stack size. The pool size means you can have more than one of these. And then when you call this, in the code, you just call it, and you get back this handle that you then can invoke start on, and this spawns a Zephyr thread. It takes care of defining the thread structure. So there's a handful of kind of hygienic cleanups to make this code a lot friendlier to use. So that's kind of the next thing to go in. Beyond that, I would say it's focusing on devices, making it work on more boards, making it work on more devices. Just a caveat from all of this is I have about a month left where this is my full-time job, and then it becomes kind of a side project again. I mean, I fully intend to keep maintaining this, to keep being involved, but additional contributions will be greatly appreciated too, and people that want to work on it. The goal here was to get enough of a core in place that we have something we can build on.
As a random note, and maybe that's a way to get the participation and the contributions going. Do you want to share a few words about your REST-based, I guess, keyboard? Okay. Is this on GitHub somewhere?
It is. I can post a link if you want. If I can stop printing. What's funny about that comment that my keyboard is I put a lot of effort into being quiet about it, because at the last governing board meeting, Anos kind of at one point in the meeting said, "David, your keyboard is really annoying." And I put a lot of effort into finding, where can I post this? I don't really know.
Yeah, we can put we'll put the link in the comments on LinkedIn and YouTube. There's actually might be our last questions, but I think this one actually, I'm shocked we didn't get to it before. Is it already possible to sort of do it, I guess, the other way around? Write a full REST module that integrates in an existing C project? I just saw examples of REST main, but what if the main is in C?
So there's actually a PR for exactly that's open, that needs a few things fixed, that instead of requiring it instead of it just automatically calling Rust main, right now you can still add C code to your project in the CMake file. This basically just allows you to configure it so that it doesn't automatically provide an implementation of main, that you can write that in C and then have the Rust code called when you need it to be. So I think that answers the question. It's like, no, technically not possible yet, but it's not difficult, and there's a PR for that.
Okay, awesome. So yeah, we will be dropping a few links, I guess, and I probably
be sure to point to the Discord channel.
Yeah, exactly. I was going to put that. Certainly, if you're not on the Zephyr's Discord, join us. Chat.zephyrproject.org will get you the invite. And there's a REST channel among many others. With that, I think, yeah, we're reaching the top of the hour. It was really great to have lots of live demos. That's for sure. Lots of live questions as well. I think we never had that many. So we will be back in a few weeks' time. As a reminder, if you want to present something, just make sure to ping me. Find me on Discord. I guess that's your excuse to show up on Discord. And yeah, David.
And the person who's asking about my keyboard, ping me on Discord.
Yeah,
and I can tell you the specific key switches that I'm using in keycaps. So
yeah, awesome. Thanks everyone, and thanks David. We will be back.
Great. Thank you.